Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to predict the electron group geometry and molecular geometry of your central atoms in the molecule. So let's go get into this. So the first thing you're going to need is a molecular geometry chart like this one. So this is one I just got off the internet, but there's many like it. So this is going to be very invaluable for figuring out what the electron group geometry and the molecular geometry is. And so you could see here that on this side here, let me position this correctly. So here you've got the number of electron groups. That's the total number of electron groups that would be bonding and non-bonding together. And so then here, the number of lone pairs is given to you here. And then in the next one, it gives you the electron pair arrangement. This would be the electron group geometry. And then here would be the molecular geometry shown here. They don't give you the names here, but some of them will give you the names. So you'll need something like that that's going to give you the electron group geometry and the molecular geometry as well as the angles. So I'll be working off of something like that. So either you kind of have it memorized, maybe your teacher, your professor has you memorize them. So that's even better if you have them memorized, or if they're letting you use a table or something, you can do that. So you should have something if you need it. So first thing I want to do, where's my marker? So here are some examples. I'm going to go over the examples and I'm going to just tell you based on what the electron group, based on what the chart is telling you, what you should determine for each central atom. So some molecules are going to have more than one central atom. Some molecules are just going to have one central atom. So let's go ahead and get started. So in A, here we only have one central atom. So we have the nitrogen, the fluorine, and the oxygen are bonded to the nitrogen. So we're going to look at the nitrogen to determine the electron group geometry and the molecular geometry. Now, the distinction between the electron group geometry and the molecular geometry is what are you counting as electron groups? Okay, so for the electron group geometry, you are counting all the bonding and non-bonding groups together, right? So you want to include the lone pairs in your count, okay? In the molecular geometry, you are ignoring lone pairs and only looking at the atoms and how they are connected. And so that will determine what the molecular geometry is. Okay. The other thing to keep in mind as well is double, single, and triple bonds all are treated equally. They're only considered as one group. So here I have a double bond that is not two groups. That's one group. Okay. So this is one group of electrons. This single bond is another group of electrons. And this lone pair here is another group of electrons. So for this molecule here, nitrogen has three total groups of electrons. When you look at your chart and you find what the electron group geometry is for a molecule or a central atom that has three total groups, you will find it is it's going to be trigonal planar. So here I'm going to put EG for electron group geometry, EGG, and that's going to be trigonal planar. Okay, now for the molecular geometry, you ignore the lone pair. So when you have one lone pair and two bonding pairs around your central atom, then the molecular geometry is going to be bent. So the molecular geometry is bent. And so with regard to angles, the bond angle here between these two, since it's a bent trigonal planar, it's going to be approximately 120 degrees, probably less than 120 degrees, a little bit less than 120 degrees. But the ideal angle would be 120 degrees because we got three groups. So it's going to be less than 120 degrees. So, but the ideal angle is 120 degrees. But it's going to be less than because the double bond takes a little bit more space. The lone pairs take up more space. But if your teacher doesn't care about that, then 120 degrees would be the ideal angle if you want to go with that. But technically, it would be less than 120. Okay. Now, this molecule here has several central atoms. So we have 1, 2, 3, 4, 5, 6. So each of these has an electron group geometry and as well as a molecular geometry. So we're going to do each one at a time. So here, this carbon here has 1, 2, 3 groups around it. Remember, the double bond is one group. Double, triple, and single bonds are treated the same. So each are one group. And here we have 3 groups, no lone pairs. So anytime you don't have any lone pairs around your central atom, then the electron group geometry and the molecular geometry will be the same. So according to your table, if you look on your table, when you have 3 total groups around your central atom, that's going to be trigonal planar. So this one here, I'll put TP for trigonal planar, and the angle is going to be 120 degrees. So same thing with this carbon here. You'll see the same thing. Has 3 bonding groups, no lone pairs. So the total number of electron groups is 3. So that means, again, that the electron group geometry and the molecular geometry will be the same. So that means that this carbon is also going to be trigonal planar with regard to its electron group geometry and its molecular geometry. And you could see the same thing for this carbon as well. 1, 2, 3 groups, no lone pairs. So again, this one is also going to be trigonal planar in its electron group geometry and its molecular geometry. And the bonding angles are going to be 120. Okay. Now, what about this carbon here? This carbon has 1 triple bond and 1 single bond, no lone pairs. So in this case, there's 2 total electron groups, no lone pairs. So again, the electron group geometry and the molecular geometry are going to be identical. Again, whenever you don't have lone pairs on your central atom, the electron group geometry and the molecular geometry will be the same. So here, that's going to be linear. And it's going to be 180 degrees. That's the angle between these 2 atoms. Okay, so that takes care of that one. Here, we have an oxygen with 2 bonds, 2 single bonds, and 2 lone pairs. So you have 4 total electron groups around this atom. If you look at your chart, whenever you have 4, not 5, 4 total electron groups around your central atom, that's going to give you a tetrahedral electron group geometry. So here, the electron group geometry is going to be tetrahedral. But the molecular geometry is going to be different because we have lone pairs. So because two of your electron groups are lone pairs, we're going to ignore that and just look at the structure. When you look at that, then you get a bent shape. So the molecular geometry for this central atom with two lone pairs, two bonds, is bent. So the molecular geometry is bent. And here we have, again, 4 bonds, no lone pairs. So again, the electron group geometry and the molecular geometry will be identical. We have 4 lone pairs, just like we said here, 4 bonds. Just like we said here, with 4 total electron groups, it's going to be tetrahedral. So here, both the electron group geometry and the molecular geometry will be tetrahedral. So this is tetrahedral, and I forgot to mention the bond, the bond angle. Here, the bond angle is going to be less than 109.5. That's the ideal angle, but because of the lone pairs, it's probably going to be pushed more closer together. In this case here, since we don't have any lone pairs, the bond angle is going to be 109.5 degrees. And then that's it for all of the central atoms for this molecule. Here for C, we have 1, 2, 3, 4 bonds around our central atom. This only has one central atom, so we only need to look at the carbon. So since we have 4 total electron groups, no lone pairs, the electron group geometry and the molecular geometry will be identical. And again, just like over here, we have 4 groups. The electron group geometry is tetrahedral, so the same thing over here. So the geometry around the carbon is going to be tetrahedral. So that's for the electron group geometry as well as the molecular geometry. The angle again is going to be 109.5 degrees between all of the atoms, the bond angles between the atoms. Okay, we're going to go to D. Here, again, this molecule only has one central atom. So the 3 fluorines are bonded to this central atom there. And let me just double check that for a moment. I forgot a lone pair there. I'm glad I caught that. So the reason I caught that is because AS is in the same group as nitrogen, and so you would expect the same Lewis dot structure for that. So here you can see nitrogen has 3 bonds and 1 lone pair. So you would expect arsenic to have 3 bonds and 1 lone pair. So just double checking that. Okay, so now that I've got the right Lewis dot structure here, you'll see here that I have 4 total electron groups. Again, if you have 4 total electron groups according to your chart, it should tell you that the electron group geometry is tetrahedral. So electron group geometry. So the EGG is let me make sure I have room, tetrahedral. Okay, so, but one of my electron groups is a lone pair, so that means that the molecular geometry is going to be different. And according to your chart, if you have 4 total groups and one of those groups is a lone pair, then the molecular geometry is going to be trigonal pyramidal. So let me write that here. So trigonal pyramid or pyramidal. Okay, so that's it for that one. For this one, again, I only have one central atom here. So carbon is the central atom. I have two sulfurs bonded to it. Each of these is a double bond, but again, we're going to treat each double bond as one electron group. So according to this, I have two electron groups around my central atom, no lone pairs. So again, the electron group geometry and the molecular geometry are identical. So in this case, according to your chart, the electron group geometry with only two total electron groups around your central atom is going to be linear. So the electron group geometry and the molecular geometry is going to be linear. And of course, for linear, the bond angle is going to be 180 degrees. I forgot to mention the bond angle for this one. So for trigonal pyramid, so for a tetrahedral, the bond angle would be 109.5 for an ideal angle, but since we have a lone pair here, it's going to be less than that. So it'll be less than 109.5. It could be like 107, but we know it's going to be less than 109.5, less than the ideal angle. Let me make sure that's clear. Okay, so the next one, F. Here we have two bonds, two single bonds, two lone pairs. So again, this molecule only has one central atom. This one with the two fluorines bonded to it. Since this has four total electron groups, two bonds, two lone pairs, then the electron group geometry will be tetrahedral. So the electron group geometry, let me draw it here. So in this case, the electron group geometry would be tetrahedral. But since I have two lone pairs, the lone pairs are going to give you a different molecular geometry. So in ignoring the lone pairs, we look at the shape of the molecule and we look at it and we see that it is bent. So the molecular geometry, according to your chart, it should say bent. Whenever you have two bonding groups and two lone pairs, your molecular geometry is going to be bent. So molecular geometry is bent. Here we have boron bonded to three iodines. We have three single bonds. Boron is the only central atom. So we only have three bonding groups, no lone pairs. So again, in this case, whenever you don't have lone pairs, your electron group geometry and your molecular geometry are identical. So according to your chart, if you have three total electron groups around your central atom, then the electron group geometry is going to be trigonal planar, which is going to be identical to the molecular geometry because we don't have any lone pairs. So here, it's going to be trigonal planar, and the what do you call it? The bond angle is going to be 180 degrees. Next, for H, again, we have 1, 2, 3 bonding groups. Remember, the double bond is treated like one group. So again, we have 1, 2, 3 bonding groups, no lone pairs. So again, your electron group geometry and your molecular geometry will be identical. And so just like with G here, with the boron, we have three groups. So again, the electron group geometry and the molecular geometry for this molecule will be trigonal planar again. So this one is also going to be trigonal planar. And the bond angle is going to be 120 degrees. Oh, did I say 180 here? That's not right. 120 degrees. Thanks for letting me know. So this is 120 degrees as well. Finally, we've got this molecule here. So again, this has multiple multiple essential atoms. So we have carbon, carbon, and carbon. These are three essential atoms. So they're each going to have their own electron configurations, their own shapes, their own molecular electron geometries, not configurations, electron geometries. So here, this carbon has 4 bonds, no lone pairs. So the electron group geometry and the molecular geometry will be identical to each other. So in this case, if you have 4 total groups around your central atom, you've got a tetrahedral electron geometry. And so this is going to be tetrahedral. This carbon has 1 single bond, 1 triple bond, so 2 groups. Remember, the triple and single bond are treated the same. So this is 1 group, this is 1 group. So we got 2 groups around our central atom, no lone pairs. So again, the molecular geometry and electron group geometry are the same. So in this case, according to the chart, if you only have 2 electron groups around your central atom, then you've got a linear electron geometry. So this is going to be linear. And if we look at the next one, this is also going to be linear because we have a triple bond and a single bond, just like this carbon. So these carbons are going to have the same geometry. So this one is also linear. Okay, and so that's it for this video. I hope this was helpful. I hope this helped clarify how to figure out whether your central atom has a certain electron configuration or molecular group geometry or molecular geometry, whether those geometries are identical or different. If you hopefully this helped you use your chart. So if this was helpful in any way, if you enjoyed this video, then please like the video, share the video, hit that like button. Also, make sure that you subscribe to my channel, hit that notification bell. When you do, make sure you click all so you'll be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you want me to help you with, if you have a topic you want me to cover, I would love to do that for you. Thanks for joining me and have a great day.